So yeah, I hope everybody had a good weekend. I feel like it was just really short, but just like the last weekend, I guess. Yeah, they've been short, it feels like, but that is all right. Just gotta get through it. So game plan for today. I believe last time, last time I for sure covered how to optimize with a Cobb-Douglas equation, but I don't think that I went into the nitty gritty of how to do it with perfect substitutes and perfect complements. So we're just going to start off with that. I'll give you some kind of general examples, and then we're going to apply it with maybe some practice problems on the midterms, right? Whether they come up or not. So let's look at a case with perfect
Yeah.
All right. You know that perfect complements are going to look something like this. Utility of x1 comma x2 is going to be a function, right, of the min between x1 and x2, right? And so given that we have a budget constraint that looks like this, p1 x1 plus p2 x2 is equal to m, we have to figure out at what levels of x1 and x2 are we going to be maximizing our utility. Okay, actually, let me turn this off because I think there's a little bit too much glare. Is that better or is that worse? Maybe someone can leave a comment in the chat. It's good? Okay, awesome. So if you guys remember what a perfect complement graph looks like, right? We have it so that we have these L-shaped indifference curves, right? Where each of these indifference curves, if you remember, has the same amount of utility. So similarly to Cobb-Douglas, we want to be on the highest indifference curve that we can still afford, right? So say that we have a budget constraint that, for example, looks something like this, right? Well, then in this situation, the indifference curve that puts us highest, right? So the highest amount of utility, while still being affordable, would be something like this, right? Does everybody kind of agree with that? And so when you think about what this means with respect to the actual numbers, we know that at each level, right, of maximization, we're going to have a pairing of x1 and x2, right, so that they kind of go in tandem with each other, right? So you can think of a bicycle. Each frame comes with two wheels, or else it's a unicycle, or it just doesn't work, okay? So given that information, the way that we're actually going to be solving these perfect complements questions is that these two terms that are in the middle, we're going to set them equal to each other, right? So x1 equals x2, right? And what this does, this essentially just locks in the ratio of x1 to x2 that we're going to need, right? So in this situation, it's going to be a one-to-one relationship, meaning that for each level of x1, we're going to have a one-to-one relationship with x2, right? So if we have 5 units of x1, we're going to need 5 units of x2, and so on and so forth, right? So given this information, right, this is really huge, right? Now, at this point, we're actually going to be able to plug it into our budget constraint so that we get P1 x2 plus P2 x2 is equal to M. We can pull out an x2, P1 plus P2 equals M. And then we're going to get that the optimal level of x1 is going to be M over P1 plus P2, right? Which is also going to be equal to the optimal level of x1, right? Because we have that they're equal to each other. Now, with that being said, this is a very general problem. And you'll notice that I kind of set it up nicely so that x1 exactly equaled x2, but that's not always the case, right? So in that bicycle example that I just mentioned before, we need 2 wheels for every bike frame, right? So this x1 equals x2 wouldn't fit for that description. So let's take a look at a specific problem. I'm going to provide numbers and we'll see whether we can work it out. So here we go. So let's see, let's say that a min function, right, where we have 5x1 comma x2, right? And so just kind of a refresher, what it means when we have 5x1 comma x2 is that we're going to need 5x2 for every 1x1, right? Because we know that we want these to be equal to each other, right? So we want this to be equal to this. And so the only way that we can have it so that that's true is if we have 5 of these for every one of these, right? So just imagine x2 is equal to 5 and x1 is equal to 1. That makes sense, right? Both sides of these, I guess, terms would equal to 5. So similarly, we're going to say that 5x1 is equal to x2. And I would just leave it like this. You can have it in terms of x2 instead. It's kind of up to you guys. Let's say that we have P1 is equal to 2, P2 is equal to 4, and M is equal to 30. Let's do 40, maybe 40. I think the numbers would work better. Okay. So with these, you guys can choose to graph it or not. That's really kind of up to you. I think that for the sake of showing it, I'm going to graph it. Because I think that for a lot of you guys, seeing it visually probably makes it a lot easier. So we're going to do that. Let's say that this is the x1 intercept. This is the x2. First, I'm going to draw my budget constraint. And we're going to say that we can afford 10 units of x2. And we can afford 20 units of x1. Right? And then they're connected by this straight line. Now, we know that for every 5 units of x2, we're going to want 1 unit of x1. So now that's going to be kind of the ratio that we're going to be showing, right? So let's say that this is 5 and this is 1, right? This right here is going to be an L-shaped indifference curve, right? Something like this, 10 and 2, right? And this isn't exactly drawn to scale, but you guys can kind of see what I'm doing here, right? 10 and 2 will be another indifference curve, something like that. And we're just going to keep going on with this 5-to-1 ratio that we see right here. Okay, so visually you can kind of see where we're going to be optimizing. It's going to be roughly in this area shown in green, right? Something along the lines of this. Okay, now with that being said, let's go ahead and let's solve this thing. So we have P1 x1 plus P2 x2 is equal to M, right? So now at this point, what I'm going to do is I'm going to kind of fill in these numbers. So 2x1, I'm going to leave it in terms of x1 because that's how we have it here, plus 4x2 is equal to 5x1 is equal to 40. And so we get 2x1 plus 20x1 is equal to 40, which means that we have 22x1 is equal to 40. And so in this case, we kind of get these weird looking numbers, most likely on a midterm, such as the one that you'll be having on Thursday. They're going to give you numbers that give you whole numbers. But for now, we're going to say that x1 is equal to 40 over 22, right? And 40 over 22 is roughly a little bit less than 2, right? And so if we look at where less than 2 is, that's kind of around here, right? Right? So this is something that you can do to just check your answer, is to see whether it makes sense when we put it on the graph, right? And so now we also know what x2 is. x2 is just going to be equal to 40 over 22 times 5, right? So 200 over 22. And 200 over 22 is going to be roughly less than 10, which also makes sense, right, given the graph. Okay, so this is kind of the way that I go about these questions. I think that this is probably best practice, but are there any questions about this? Hopefully you guys have seen enough of these problems to feel comfortable, but It's something that I hadn't formally introduced yet. So
Could you just explain where the 5 came from at the end, where you multiply 40 over 22 by 5?
yeah, so it comes from this relationship right here, right? Because we know that we consume these two in pairings, right? Where we're gonna need 5x2 for every 1x1, right? Then in this situation, right, I know that in order to find the amount of x2 that I need, given that I have x1 solved within the budget constraint, I just multiply by 5.
I see. Thank you. Yeah.
Yeah. The MRS test, could you maybe talk about what the MRS test is? The only thing I could really think about for MRS tests is that when we're on this portion of the indifference curve, the MRS is 0. And when we're on this portion of the MRS, of the indifference curve, the MRS is infinity. Is that what you're referring to, Caesar?
No, not really. So I'm just having a, just want to make sure I get this right. So when we do an MRS test on a particular, well, we're checking for it, we have to look at what happens to the function when x1, where x goes up and y goes down, right?
Oh,
That's
I
what we want
see.
to know.
Are you referring to diminishing MRS?
Oh, yes, yes. How do we check for diminishing MRS?
Yeah, so in this situation, you're actually not going to be getting diminishing MRS. Diminishing MRS is really just a test for when we have quasi-linear or when we have perfectly, not perfectly, strictly convex indifference curves. So like Cobb-Douglas equations. So you wouldn't actually be using an MRS test in this case, right? You're basically just gonna be finding the kind of intersection between the budget constraint and then the kinks, right? So it's gonna be undefined. To answer your question, James.
Oh, okay, yeah. But so an MRS test, we disregard the MRS test with perfect complements and also perfect substitutes. Do we even look at the MRS test with perfect
The
substitutes?
MRS is going to be an important part of perfect substitutes, but it's not used in the way that you typically have been using it, right? Where as you increase x1, your MRS should go down, or as you decrease x2, your MRS should go down. It's a little bit different than that, right? Because we don't have diminishing marginal rate of substitution. But I'm going to get into that with perfect substitutes. But are there any questions about perfect complements before we get into it? Okay. All right. So with that being said, I'm going to move on to perfect substitutes. And so perfect substitutes, the MRS is going to be important because it reveals to us kind of this concept of bang for our buck. So Stephen, you asked a question about would the optimal x1 be divided by 5? No, so you're going to multiply the optimal x1 by 5 to get the optimal x2 in this past question. Yeah, and that's because of the fact that we needed 5x2 for every single x1, right? There was a 5-to-1 relationship. All right, so moving on, let's look at perfect substitutes. Okay, the key thing about perfect substitutes is that when you find the marginal utility of either x1 or x2, it's just going to be a constant term. And the reason why is because perfect substitutes follow a linear relationship, meaning that their coefficients are going to be constants, right? So typically, you'll see a perfect substitutes indifference curve looks something along the lines of x1 plus x2, right? And so in this case, if I were to find the MRS, it would just be 1, right? Meaning that I prefer each of these equally. And so if I were to exchange 1x1, I would be perfectly content with getting 1x2 back, right? And so hopefully you guys can kind of see that with perfect substitutes, the MRS is always going to be the same no matter where we are, right? in terms of how much x1 and x2 is, right? So it doesn't really depend on the bundle that we have, okay? And so, right, given that, and given P1, x1 plus P2, x2 is equal to m, right? Because of the fact that we don't really care whether we have x1 or x2, because of the fact that they provide the same amount of utility to us, right? That's where the prices are really going to come in handy. Because say I have oranges and apples, right? And I prefer them equally to each other, right? But say oranges are $1, whereas apples are $2, right? If I prefer them equally, but I can afford more oranges, then I'm going to consume only oranges, right? And so that's kind of the thinking between, with regards to perfect substitutes, is that we're either going to be consuming all of one good or all of the other. Now, there's a case in which you're indifferent between a certain combination, and I'll get into that, right? But for now, assume that you're going to prefer one good or another, right? So let's take a look and let's see. So in this case, we know that our budget constraint is going to look something like this, right? Where it's going to be a straight line. Okay, so we don't exactly know what the slope of this is because of the fact that we don't know what the prices are. Okay, now in this case, we're also going to be having x1 and x2. And because of the fact that the budget constraint, or not the budget constraint, because of the fact that the MRS is going to be constant throughout, we're also going to be getting a straight line for our MRS, right? And so this is just kind of an example. This is not taking into account any of these numbers, right? This is just showing what in general this is going to look like, right? And so remember that we have infinitely many indifference curves, meaning that I also have one that looks like this. I have one that looks like this. And I have one that looks like this, right? And so the only thing that is important with the indifference curves is that they follow this ratio of the marginal utility of good 1 over the marginal utility of good 2, right? So in this case, as long as their slope is 1, or I guess -1, because it's downward sloping, as long as that is the slope, it's a legitimate indifference curve. So without providing any numbers, am I going to be consuming all of x1 or all of x2 in this case? And you guys should be able to answer this just given the graph. All right, I'll give you guys around 10 seconds and hopefully I can get some numbers or some answers. All right, I'm seeing some x1s. All right, does anybody want to explain why it's all x1? You guys have the correct answer, but I want to hear your guys' reasoning. So does anybody want to step up?
I can try to explain it.
Yeah, go ahead.
So the budget constraint touches the indifference curve in 2 places, and they're both on the, one is on the x-axis, one is on the y-axis, but you'd prefer the one on x1 on the x-axis because it's like the indifference curve is farther out, so your utility would be higher if you buy all of x1.
Yeah, so exactly what you just said. And so for those who maybe don't quite understand what her answer really kind of encapsulated, essentially what she was trying to say is that you see how, and it can be a little bit messy because I'm not sure how well you guys can distinguish between the colors. But essentially we have one budget constraint, right? We have one budget constraint that's given by the slope of P1 over P2, right? And so, or P2 over, I think it's P1 over, why am I getting confused by this? Anyways, we have a budget constraint, right, that's given, right? Yeah, so it is kind of hard to tell the lines apart. But essentially, you see how our budget constraint is touching, right, a lot of different indifference curves, right? There's an intersection here, there's an intersection here, it's touching right here, and it's also touching right here, right? So essentially, each of these points that is a point of intersection, right? And maybe it'll be easier to see in green. Each of these points right here provides the same amount of utility, okay? Or excuse me, they don't provide the same amount of utility. They cost the same amount of money, right? Meaning that each of these points right here are equally as affordable. However, that being said, they don't provide the same amount of utility, right? You guys can clearly see that this point right here provides less utility than this point right here, which provides less utility than this point right here, which provides less utility than this point right here, right? Because you guys can see that this indifference curve right here is the furthest out, right? Meaning that you're paying the same amount, but you're getting more utility. You're getting more bang for your buck in this case, all right? And so there's a general rule that when the slope, so when the slope of the MRS is greater than the slope of the budget constraint, right, then we're going to consume x1, okay? Similarly, right, if I had it so that the slope of the MRS was less than the slope of the budget constraint, you would notice that kind of the exact same thing that you're seeing here, just flipped, would be occurring for x2, right? Meaning that when the slope of the MRS is less than the slope of the budget constraint, right, we're going to consume x2, okay? And so this is like a cool trick to remember, but I don't think it's essential that you remember. I think that if you're just able to draw it out, you'll be able to see. But you kind of want to think which indifference curve that touches the budget constraint is the furthest out, right? That's like the general rule that you're going to want to choose. Now, there is a specific case in which the MRS could be equal to the slope of the budget constraint. And when that's the case, you're indifferent between any combination of x1 and x2 as long as it's equal, right? Or as long as it's on the budget constraint, right? So if you think about that example that I provided earlier, where I have apples and oranges, and they each provide me 1 unit of utility, meaning that I like them equally, and they're the same exact price. Well, if they're the same exact price and they both provide me the same amount of utility, I'm good with any combination of those apples and oranges as long as I'm using up all of the money that I'm allocated, right? So say that I have $10. I'm equally happy between 10 oranges and 0 apples, 0 oranges and 10 apples, or 5 oranges and 5 apples. As long as they both equal to 10, then I'm happy. Does that make sense, guys? So that's kind of a unique case. Slope of MRS for is plus. Could you explain what you mean by plus or equal? Yeah. So yeah, essentially the situation I'm describing right now is when the slope of the MRS for perfect substitute is equal to the price ratio. All right. That's when we're going to be indifferent between our consumption as long as we're using up all of the income that we're allocated. Okay. Now, for this kind of question, let's provide maybe some numbers to it. So let's erase this, and we're going to do a number that actually has, or we're going to do a question that actually has numbers. So let's say that this is 6, and then this is 5, right? And we'll say that P1 is equal to 4, P2 is equal to 10, and M is equal to 50. Okay.
Wait, Eric, real quick, on the last kind of thing you were explaining, why would you want X2 even if the MRS is less than your budget constraint? Because don't you always want like things that are more like up and to the right?
Oh, so I'll kind of just draw it real quick, right? Say that this is my budget constraint, and say that the slope of my MRS is less than the slope of my budget constraint, right? So we have a situation like this, right? You see how being on this one is higher than being on this one right here?
Mm-hmm.
That's kind of the exact same thinking. It's just kind of flipped, right? So this
Okay.
is a situation in which our MRS is less than the slope of the price ratio.
Okay, that makes
Does that
sense.
answer your question?
Yeah.
Awesome. Okay. So let us kind of get into this this question. I like to always draw, and I could have maybe picked better numbers. Actually, let's just change it to a 5, so it's not super messy, right? So I'm able to afford 10 units of good 2. I'm able to afford, or 5 units of good 2, and I'm able to afford 10 units of good 1. All right. So this is P1 over P2, which is equal to 1/2, right? So slope of price ratio, and this is the absolute value, is equal to 1/2, right? So we got that established. And so we know that for this situation, the MRS is equal to marginal utility of good 1 over marginal utility of good 2, which in this case is going to be equal to 6 over 5, right? Meaning that, right, for every 6 units of good 2, I'll be content with 5 units of good 1, right? Because if you think about it, you want to just plug in numbers for x2 and x1, which make it so that this right here is equal to this, right? So you see that 6 units of good 2 provides 30 utility, and 5 units of good 1 provides 30 utility, right? Which is the point of indifference between the two, right? So that tells us that I'm going to have a slope that's going to be greater than 1, right? And so you really don't even need to draw it that precisely, because of the fact that we know the relationship between our MRS and our price ratio. So the absolute value of the slope of the MRS is going to be 6 over 5, which I guess technically doesn't need to be, I don't need this here. But you see how I can make a comparison between the two, right? And it looks something like this, right? Where being on this indifference curve, right, is going to be much better than being on this indifference curve, okay? And you guys can kind of plug in numbers also. So another way of going about this kind of question is saying, well, if I'm able to afford 10 units of good 1, right, I want to plug that in to my my utility function. So I'm able to afford 10 units of good 1. So all x1 would give me 60 utility, and all x2, which I'd be able to afford 5 units, would give me 25 utility, right? So these are both legitimate ways of solving this question, right? There's going to be multiple ways of going about it, but you know, hopefully that as you guys start to do more of these problems, which hopefully you guys have been, you guys are going to be able to start kind of doing this in your minds and sort of just being able to visualize what's going on between the MRS and then the price ratio. Are there any questions about that?
Wait, how did you get 60 and 25?
Yeah, how does x2 equals 25?
That's if I consume only x2, right? If I consume only x2, then I'm consuming 5 units of x2, right? Right? You guys can see that that's the most I can afford of x2.
Yeah.
And if I plug in that 5 into x2, I get 5 times 5 is equal to 25.
Oh, I see. Yeah, you're plugging it back into the original equation.
Yeah, exactly. All right. Does that make sense, guys?
Yeah, so the steeper the indifference curve is, if it's relative to the MRS, if it's steeper than the MRS, then we prefer the first one, the first good, right? And if
Yeah,
it's
yes,
smaller
yes.
than the MRS, then we prefer the second good.
Yes, exactly, yeah.
Okay.
All right. So I think that kind of covers it. I do want to talk about quasi-linear because they can be a little hard to understand. But I think quasi-linear is probably the easiest to actually do in terms of like the algebra behind it. So a quasi-linear utility function, and actually let me just write it up here so that people know. So quasi-linear. You guys might have seen it. You don't go over it a ton in lecture, but I think quasi-linear is super important when it comes to midterms because I see it in pretty much, I would say there's at least one question in like every 2 midterms. That there's no empirical evidence of that, but that's kind of just my general feeling. But a quasi-linear utility function is one that has some sort of curvature to it, but there's also going to be a linear term that's attached, right? And so what I mean by that is something that looks like, say, the square root of x1 plus 5x2, right? And you'll notice that this is quasi-linear because of the fact that there's diminishing returns to the variable that has the curvature to it, right? So what I mean by that is essentially the exponent is going to be less than 1, right? And that's kind of a defining feature of quasi-linear is that there's going to be a exponent that's less than 1, which is going to allow us to solve this, right, with diminishing marginal rate of substitution. And if that doesn't quite make sense, just kind of hold back, right? Another way of, or basically there's several different ways that this could be expressed. They could also be the natural log, right? Yeah, so to answer your question, Becky, if the exponent is squared, then we're going to start to get increasing MRS, right? And essentially, we're only going to want to consume x1 pretty much, right? Because if you square it, then that basically exponentially increases the utility that you get from it, right? So to answer your question. You could also see something along the lines of natural log of x1 plus 5x2. It doesn't need to be a 5. It could be any constant term here, right? But essentially, when you solve these questions, right, you're going to solve them in the same way that you would solve just a regular Cobb-Douglas, right? And I actually have no idea how to graph these. I'm sure that you could definitely graph them out. I just never learned how to, and I don't think it's really important that you know how to. If anything, you just plug in coordinates and see what the output is. But you don't need to do that. The way that you would go about solving one of these, so say that we have a budget constraint P1 x1 plus P2 x2 is equal to m, right? And we're going to actually leave it in general terms for now, okay? What we're going to do is we're going to find the MRS of this quasi-linear, right? And the MRS of it is going to be equal to the marginal utility of good 1 over the marginal utility of good 2, right? So what this kind of equals out to, and let's use this one, right? Let's use this one. So the marginal utility of good 1 is going to be 1/2 x1 to the negative 1/2, right? Over the marginal utility of good 2, which is just going to be equal to 5, right? And so what this kind of equals out to is 1 over 2 times the square root of x1 over 5, which if you guys saw my correction, I was able to kind of walk through it, which is just going to be equal to 10, right? Because you just multiply by the reciprocal. So that was good on you guys math-wise. That was bad on me. But pretty much you get an MRS that looks like this, right? And this actually has diminishing marginal rate of substitution if you take a look at it closely, right? even though there's only one term in here, right? If x1 goes up, my MRS should go down, right? And that's exactly what happens in this case, right? As x1 increases, the denominator also increases, which is going to bring the value of the MRS downwards, right? And so because of the fact that we have DMRS, right? Because of the fact that we have DMRS, we're going to be able to set this equal to a price ratio, right? And solve by doing that, right? So in this situation, I have MRS equal price ratio. So MRS equals to the price ratio is going to be 1 over 10 times the square root of x1 being equal to P1 over P2. All right. And I want you guys to really pay attention to like the next few words that are going to come out of my mouth. What you notice is that the MRS only has one single variable in that, right? And that's a defining feature of all quasi-linear MRSs, is because of the fact that one of the terms is linear, right? This linear term, whether it's x1 or x2, it doesn't really matter, right? x1 or x2 will, actually it might matter. Let me take that back. It might matter, but that's something that you'll be able to figure out as you work through it. But pretty much one of these variables is going to get dropped when we find the marginal utility, right? And so because of the fact that there's only one variable here, we're actually going to be able to solve for the optimal levels of x1 simply by setting it equal to the price ratio, right? We don't need to plug it back into a budget constraint. We're going to be able to solve for the optimal amount just by setting it equal to P1 over P2, right? This whole thing equal to P1 over P2, right? And then from there, whatever money that we have left is just going to be allocated towards the other good, okay? So let's work through a problem. So if we were to actually work this out, you would get something like P2 is equal to 10 P1 square root of x1. And so square root of x1 is equal to P2 over 10 P1. And so x1 star is going to be equal to this whole thing squared. Okay. And then from there, once we know the optimal amount of x1, we can plug it back into our budget constraint right over here and solve for x2. Okay. So let's do this. Let's do a problem with numbers. And in this case, let's use the natural log, because I think the natural log could be a little bit more fun to work with. So natural log of x1 plus 5 x2, right? And you'll remember that if it's like 2 times the natural log, the derivative is just 2 over x1, right? So hopefully you guys are still comfortable with your like derivatives. So let's say that we have P1 is equal to 2, P2 is equal to 5, M is equal to 20, okay? And we're given this utility function right here. The way that you go about this, right, first and foremost, is you find your MRS, right? And this is just a general tip of advice, is that aside from perfect complements, the first step that you're always going to take is pretty much solving the MRS. Like if you have nowhere to go and you're kind of lost, find your MRS, and maybe from there you'll figure out where to go. If not, they'll give you some partial credit for just writing this MRS down. I'm almost sure of it. So the MRS, right, is going to be 1 over x1 divided by 5, which is going to be 1 over 5x1, right? We do our marginal rate of substitution check, which is I think what you were talking about earlier, I think Caesar. We check to see whether the MRS goes down as x1 goes up, which it does. And so because of the fact that we have DMRS, we're going to be able to set our MRS equal to our price ratio, right? So 1 over 5x1 is going to be equal to 2 over 5, right? And this will look something like, or oops, this will look something like 5 is equal to 10 x1. And so x1 star is going to be equal to 1/2, right? And this is the optimal amount of x1, right, that we're going to have already. And so there's no need to do anything else with x1, right? The only thing that we're now going to be looking forward to is how much x2 are we going to need, right? And so from here, if I have my budget constraint, which I do, I have P1 x1 plus P2 x2 is equal to m, right? If I start to plug in numbers, I get 2 x1 plus 5 x2 is equal to 20, right? x1 is just equal to 1/2. So I'm going to fill this in right here with 1/2, right? And this cancels out to 1. And so I get 5 x2 is equal to 19, right? I just subtract 1 from both sides. And I get x2 star is equal to 19/5. Okay? And that's going to be your optimal bundle, right, of x1 and x2, right? And so there's actually going to be something that you'll want to know about these quasi-linear functions is that with the quasi-linear functions that we have, we're basically going to spend all of the money that we have on x1 up until we find the optimal amount of x1, right? So in this case, we only needed $1, right, to consume the optimal amount of x1, right? But say that we only had 50 cents, right? This is just kind of hypothetical. If we only had 50 cents for our question, right, then all 50 cents would have been allocated towards good 1, right? And we would have gotten no good 2. In the case where we only had $1, we only would have bought good 1, right? So pretty much you spend as much money as you can on good 1 up until you've consumed this optimal amount, which happens to be 1/2, right? And then after you've reached this optimal amount, right, then you can start buying good 2, right? So you buy good 1 first, and then you buy good 2. To answer your question, Sam, I could have. I just would have had to make sure that I had a negative here. So basically, the only thing that you're really concerned about is that the signs match up. So I could have done negative and negative, and the negative was, they would have canceled out. But that's just kind of how I do it. So 19 is not M, 20 is M, but when I kind of account for how much I've allocated towards good 1, I essentially have $19 to spend on good 2, right? After I bought my good 1. Does that make sense? All right, awesome. I might go a little bit over. I want to talk about demand functions, and I also want to talk about scalar and variance a little bit and how they relate. So I'm not sure whether they pop up this early in the class. I think they probably do, but you guys might have seen demand functions where, say, the demand function for x1 with inputs p1, p2, and m, right? Well, essentially what this means is that x1 is a function of p1, p2, and m, meaning that depending on what my levels of p1, p2, and m are, that'll determine how much of x1 I'm going to be able to afford, right? So essentially, you can think of a demand function as being what the demand is given certain inputs, right? Whereas quantity demanded already assumes what the inputs are, and so you'll get a static number, right? So a demand function is kind of, it's fluid in that you don't essentially know what our inputs are, whereas quantity demanded already assumes what our inputs are. Hopefully that kind of made sense. If not, maybe my explanation here will kind of clear the air. So how do I even find my demand function, right? Finding your demand function is actually a lot easier than what maybe you guys think. And I'm not sure how well they covered in class, but it's actually really easy once you kind of get a hang of it. So we're gonna look at what my utility function is, right? Let's say that we just have a classic Cobb-Douglas, x1, x2, and we have p1, x1 plus p2, x2 is equal to m, right? So this is about as general as it can be. The way that you find your demand function is, first off, you find your MRS. In this case, that's x2 over x1. You find your price ratio, which in this case is p1 over p2, and you set those equal to each other, right? Given that we have DMRS, which we do with Cobb-Douglas, right? So you set these two equal to each other. x2 over x1 is equal to p1 p2. And because we're looking for x1, I'm going to want x1 to be in my function, right? So you'll kind of see what I mean in just a sec. So I'm going to solve for x2 because later on I'm going to plug in x2 back into my budget constraint. So x2 is going to be equal to x1 times p1 over p2, right? And so now when I plug this back into here, I'm going to get something that looks like p1 x1 plus p2 times x1 p1 over p2 is equal to m. And so now hopefully you see why I had it right in terms of x1 is because eventually I want there to only be x1s in my budget constraint equation, right? And so from here, there's some easy cancellation, and I get 2p1 x1 is equal to m, right? And so now my demand function for x1 is, as a function of p1, p2, and m, right, is just going to be equal to m over 2p1, right? Where now I kind of know exactly what my my consumption of x1 is, and I don't even need to know how much x1 or how much x2 I have. I only need to know how much m and how much p1 are, right? And let me shine that down. And so this kind of goes into the idea of the income share thinking kind of concept that you guys have been introduced to, where I'm gonna erase some stuff right here. Actually, I can
question real quick. The MRS that you use, you put x2 over x1, and I've seen it, when sometimes, most of the time we put x1 over x2. When do we know how to use which one?
Well, x2 over x1 is just the marginal utility of x1 over the marginal utility of x2, to answer your question. So it's always going to be the marginal utility of x1 over the marginal utility of x2, right? And what that ends up being is not always known, but that's kind of what this turns out to be, right? I want to quickly go over income share, right? And I'm going to go over it really quickly. Pretty much income share, when you have x1c, x2d, when you have these Cobb-Douglas equations with exponents c and d, we're going to know that the optimal amount of x1 is going to be equal to c over c plus d times m over p1, right? This is something that is probably in your textbook and probably in your notes, but it's something that's, it's interesting to remember because it's kind of like a shortcut in a way where right away you know how much x1 is going to be, right? I think that this is somewhat unnecessary if you're already comfortable with setting your MRS equal to your price ratio, right? but this is something that works for Cobb-Douglas, right? And I don't want to kind of confuse you guys and introduce new concepts, but I think that this is something that can be applied if you have these certain criteria. Let's see. Let's see questions. So to answer your question, Becky, yes. So you isolate x1 or x2, and that's going to be depending on what you're looking for. So if I had x2, right, if I was looking for x2, then I would have, at this point, I would have isolated x2 into here, right? So that's a good question. Sam, to answer your question, yeah, that's exactly why. So if whoever asked that question about why it was x2 over x1, Sam's explanation is perfect. Ryan, there might be a shortcut. I wouldn't bank on it. I don't believe so. But also you could do your own kind of investigation. But for quasi-linear, because the steps are pretty simple, I would just kind of follow those steps that I gave. And so the key thing that I want you guys to know about demand functions is that demands are fluid based on what P1, P2, and M are, right? So you notice that X1 star, right? I don't exactly even know what it is yet. I just kind of know like what it could be given certain inputs, right? So, and you could do the exact same thing for X2 as well. Now, I don't want to take up too much more of your time, but I'm going to talk about scalar and variance in my office hours, which are going to be right after. So if you guys are interested in that, feel free. I don't see scalar and variance pop up that much, but I think it's an interesting topic.
Do you record your office hours? Like you do these?
I don't record my office hours. So
I gotta go because I have my discussion lab right now, but I want to hear that. So how do I do that?
Actually, you know what? What I could do is I could just go over it right now, and keep recording, and then it'll be at the very end of this recording.
Oh, where do I find this recording?
This is on the. So I've actually been getting a lot of questions about this. All my recordings are posted onto the CLAS for Econ 10A Gaucho space, which I believe you guys had the option of signing up for when you first enrolled in the CLAS. So when you go onto courses on Gaucho Space, you can search for this. I would just type in CLAS and 10A, and that's typically like enough keywords. But yeah, so all my lectures do get posted. I don't know. I think if you guys really are interested in knowing where to get access to it, I would email this person that I'm going to drop in the chat. He's the coordinator. He's the coordinator that kind of handles all the stuff that I do, and he's in charge of the Gaucho space. So if you want access, I would definitely email him. I think that his email should pop up if you type in binfam onto your mail, or you could find them on the CLAS website. So yeah. Also, just real quick, I will talk about scalar and variance, but are there any questions about demand functions or income share? I know that I've kind of been rushing this, and I know that people have to go, but I am open to answering questions. Okay. Sounds like there's no questions, so I'm just going to talk about scalar and variance for now. It will be recorded, or if you guys have nothing to do, you guys can just kind of listen to me talk. But scalar and variance does refer, or it does kind of tie back to demand functions, and so that's why I think that they're an interesting thing to kind of look at. And the way that we solve them is pretty straightforward. So I think that they're also something that they're fun problems to solve. So scalar and variance. You might also hear about them being referred to as like homogeneity of degree 0. I have no idea what that means or what that refers to, but the terms are kind of interchangeable. So kind of what I just covered about demand functions is that they're functions, right, of P1, P2, and M, right? Where P1, P2, and M are inputs that are going to determine what my X1 is, okay? And so something that I'll just kind of briefly go over with regards to scalar invariance is that when you have a demand function, right, and say that I'm currently consuming 5 units, right? If I doubled my prices and I doubled my income, right? Sure, I have twice as much money, but also prices are twice as much, meaning that you would expect this to still be equal to 5, right? You can kind of think about it as if inflation, right, and if interest rates, actually maybe that's not the best example to use, but essentially if I doubled my money and prices doubled, essentially kind of everything is the same relative to each other, and so how much I consume is going to stay the same. Now what scalar invariance does is it tests to see whether my demand functions are consistent with what should happen, right, given price changes. So how we do it is, say that I have a demand function that looks something like m squared over p1 squared times p2, right? This is kind of a weird looking one, right? Yeah, the MRS would be the same, Aaron. Say that this is something that we get just for example, right? I want to see whether this demand function is consistent with how you would expect preferences to kind of work out, right, in the normal world. So essentially, if I double my prices and I double my income, do I still consume the same amount, right? So let's say that in this situation, right, say that I double, or not necessarily even double, but I multiply by some constant that we're going to call lambda, right? So x1 times, or x1 as a function of lambda p1, comma lambda p2, comma lambda m. And what we're going to do is we're actually going to stick this lambda as a constant in front of whichever variables it's attached to, right? So in this case, I would get lambda m squared over lambda p1 squared times lambda p2, right? And essentially what I'm going to do is I'm going to pull out these lambdas and see whether there's any left, right, as I pull them out. So this is going to be equal to lambda squared over m times lambda to the third p1 squared p2, right? And so notice that after all my cancellations, I'm going to be left with m squared over lambda p1 squared p2, right? And this right here, this is the demand function that we started off with, but notice that there's still a term that's going to be added there. And so essentially, because there's a term that's still in there, right, that's going to tell us that my demand function changed, right? Or essentially, you can think of it as my demand changed, right? Given that you wouldn't expect anything to happen, right? So lambda is just kind of a hypothetical constant, but typically I like to think of lambda as being equal to 2, right? And so, right, essentially there's still a 2 that's going to be remaining here, right? Even though you would expect that your demand functions stay the same. So hopefully that kind of covers it. If you have questions about it, come to drop in. But I do need to kind of wrap this up. This might pop up on the midterm. I don't know for sure. That's why I kind of covered it, but I wouldn't spend too much time learning about it, is what I would say. but whether it pops up or not, I don't quite know.
Wait, where did you get the m squared over p1 squared p2 like originally?
This is just a random, I just came up with it.
Oh, okay.
Yeah. Okay. So, as I said, if you guys have any questions, come to my drop-in. Otherwise, I do have to wrap this up. But yeah, I'll see you guys on Wednesday, and we're gonna go over a practice midterm. So yeah, see you guys then.
Thank you.